Hello, this is Team Terpsichore, and this is our FDR comprehensive presentation. So since the Industrial Revolution and the advent of coal-powered steam engines, human innovation and progress have vastly increased the volume of greenhouse gases emitted into the atmosphere. It is estimated that between 1750 and 2011, atmospheric concentrations of carbon dioxide increased by 40%, methane by 150%, and nitrous oxide by 20%. In the late 1920s, we started adding man-made fluorinated gases like chlorofluorocarbons, or CFCs, to the mix of these other greenhouse gas components. In recent decades, this issue has only gotten worse. Of all the man-made emissions, carbon dioxide, which is the most abundant greenhouse gas released by human activities and one of the longest lasting, approximately half of carbon dioxide was generated in the last 40 years alone, and in large part due to fossil fuel combustion and industrial processes. Earth's greenhouse gases trap heat in the atmosphere and warm the planet. The main gases responsible for this greenhouse effect include carbon dioxide, methane, nitrous oxide, and water vapor, which all occur naturally, and fluorinated gases, which are synthetic. In a few decades, greenhouse gases, mainly in the form of CO2 emissions, have increased at alarming rates as a result of global growth and resource consumption. To uncover the major sectors where these emissions originate, the graphic on the right pulls data from the 2016 Climate Watch and World Resources Institute Our World in Data article, when total emissions reached 49.4 billion tons of CO2 equivalents. Additionally, the Energy Information Administration says that the U.S. residential sector accounts for 21% of all energy consumption and is responsible for 20% for countries' carbon emissions. The bar on the right illustrates the total number of housing units in the United States from 1975 to 2020. We can observe a large increase in housing units from 1975 to around 2010, and although the graph seems to indicate a plateau, we can actually observe that the number of housing units are still slowly growing to this day. According to the data for 2020, there were approximately 140.8 million housing units in the United States. This is significant because in the context of greenhouse gases, the emissions from a single household is multiplied by such a large factor that any change in energy consumption trends will have noteworthy consequences. Globally, heat accounts for 50% of all energy consumption and 40% of energy-related carbon dioxide emissions. In the US, 38% of greenhouse gas emissions from residential housing is produced from heating and cooling rooms, while an additional 15% is from heating water. The thermal energy produced within the household is then lost to the colder outside environment due to conduction. We're mainly interested in climate zones where households experience cold weather conditions because the colder the weather is, the faster the rate at which heat loss occurs. According to the graphic about continental U.S. climate zones, we can observe that roughly half of the United States experiences snow or extreme cold weathers, making approximately 70 million households that experience heat loss at a greater degree. Now, heat loss occurs in many different areas in the home. 5% through ceilings, 17% through frame walls, 1% through basement floors, 3% through doors, 16% through windows, 20% through basement walls, and 38% through cracks in walls, windows, and doors. Because that heat is being lost to the colder outside environment, homeowners will tend to turn up their heating appliances in order to maintain a certain indoor temperature. In colder environments, households may need to compensate in a greater degree by producing more heat in a house than a house located in a warmer climate zone. Residential homes ultimately produce greenhouse gas emissions due to their heat production, and this can result in long-term effects including global warming. Since it's not feasible to completely shut down all U.S. residential housing units from producing heat, alternative solutions must be explored in order to conserve energy on a national level starting in the individual household. Now, with cold and sleet covering your home in certain climate zones, homeowners may be more prone to turning up their heating appliances to warm their indoor temperatures. However, before increasing a home's heating bills, it may be helpful to look at where the home loses the most heat and to see if you can insulate it better. The more you can insulate the home, the less warm air will escape, and the less your furnace will have to work to heat your home. Not only will this keep your heating bills down, but your HVAC system will actually last longer. If you do add insulation in your home, it can also benefit you in the hot summer months by helping retain cooler air in your home longer. Now, the EPA estimates that homeowners can save an average of 15% on heating and cooling costs, or an average of 11% on total energy costs, by air sealing their homes, adding insulation in the attics, floors, over crawl spaces, and accessible basement rim joists. Heat loss and cold air infiltration can be greatly reduced, and the heating system can be made efficient by using a variety of cost-effective solutions, such as types of windows, using blinds, drapes, and things of that nature. Now, with all the solutions listed, it is worth exploring a mechanical electrical design that provides similar thermal energy conservation techniques. The only constraint that would prevent the use of our solution would be if the monetary cost of our solution far outweigh the monetary cost of manual installations, as well as not providing enough benefits in terms of thermal energy conservation. With all that being said, our project definition is as follows. The Energy Information Administration says that the U.S. residential sector accounts for 21% of all energy consumption and is responsible for 20% for country's carbon emissions. Globally, heat accounts for nearly half of all energy consumption and 40% of energy-related carbon dioxide emissions. In the US, 38% of greenhouse gas emissions from residential housing are produced from heating and cooling rooms, while a further 15% is produced from heating water. Therefore, heat loss is a big contributor to increased greenhouse gases. The problem is constrained to climate zones in the US that experience cold weather conditions. And as of 2020, roughly 70 million housing units in the US experience these conditions and are impacted by heat loss to a greater degree. Now, heat loss can be quantified in many different areas of the home: 5% through ceilings, 17% through frame walls, 1% through basement floors, 3% through doors, 16% through windows, 20% through basement walls, and 38% through cracks in walls, windows, and doors. Now, the EPA estimates that a homeowner can save an average of 15% on heating and cooling costs, or an average of 11% on total energy costs, by air sealing their home and adding insulation in attics, floors, over crawl spaces, and accessible basement rim joists. Because the amount of heating and cooling costs saved is directly proportional to the amount of heat loss that is mitigated, success can be measured by both the heating/cooling costs and heat loss mitigated compared with and without the solution. The key constraint that would prevent the use of our solution would be if the monetary cost of our solution was greater than the monetary cost of manual installations.
To start the blind system, we'll talk about the housing, hardware, and the mechanisms that are relevant to blind tilting and raising. So to start, we need to design our own compartment. This is because the blind compartment that we bought was too small to fit our motors and their mounting hardware. Our blind compartment was designed so that it could be laser cut. There on the bottom is the base, and on top is the side. The base and side will fit together by using a box joint, which is those teeth on the top and bottom of each side. And then the square holes that are cut onto the sides will be used for wire management to ensure that they do not get caught by any of the moving parts with our motors. And then on the base, we have the circular holes for mounting and for strings to pass through the blinds. They'll be just mounted using nuts and bolts. So one of the two systems in our blind compartment is the blind tilting system here. All these components can be commonly found in a typical Venetian blind set, which is the most common type of blinds probably found in your home. Most blind cradles are fit to the housing that they come in, so it wasn't an option for us to use the cradle from our blind set that we bought because we designed our own laser cut compartment. So to fix this, we made our own blind cradle, and this is done by using the three laser cut components on the very left-hand side and then they were epoxied and put together, and it's rigid enough to hold the blind drum and the weight of the blinds. In the production model, though, the cradle will be manufactured using preferably molded plastic so that the strength is increased and so that it is fit in our blind system better. However, the blind drum and the shaft that passes through them are taken directly from the blind set and are retrofitted to fit within that blind cradle. Lastly, the image on the very right shows the completely configured blind tilting assembly by itself, with the 2 blind cradles and 2 blind drums and the shaft that passes through. So the other mechanism that we need in our blind compartment is the blind raising and lowering mechanism. It will be done by using a spool such as this one, directly coupled to the output shaft of a motor. In the worst case, this spool is going to hold the entire weight of the blinds, so it's important that it does not break or deform under torsion, because if it deforms too much, then that will cause the actual blinds to sag by themselves. So the maximum torque that we expect on the spool is calculated here, 0.061 Newton meters, using the density of oak. And the analysis shows that it will not break, or we will not expect large amounts of torsion where the actual strings will sit, which is where those purple arrows are. The maximum amount of torsion is on the very outer edge of the spool, which is not critical to the design and function of our part. This spool here is the production model, and it will be attached to the motor's output shaft via set screw. However, we will not be able to manufacture this for the prototype design. So the prototype will use a spool from the blind set, and will be attached to the output shaft using, it will be press fit to the output shaft and will be strengthened using epoxy. So here's the motor that we chose that will power both of the previous systems that I discussed. It is a NEV-REST orbital gear motor. The gear ratio is high so that it is difficult to backdrive. We don't want it backdrivable in this case because the torque, if it's too backdrivable, then the torque from the blinds, the blind weight will spin the motors, which will cause the blinds to droop slowly by themselves. But we want to maintain the blind height that we actually want the system to set it to. So then the stall torque of this motor is also 2,400 ounce-inches, which is sufficient enough to overcome the weight of our blinds for lifting and tilting purposes. Here's the complete configuration of the blinds compartment with both motors and their respective blind systems. The motor on the right side is connected to the tilting system via a flexible shaft coupler. It was chosen to drive this shaft from the motor for reduced complexity. To do so, the output shaft of the motor needs to be raised to the height of the tilting shaft and will be done so by using multiple pieces of acrylic. The motor in the middle will be used to raise and lower the blinds using the spool, as previously mentioned. The strings coming from the spool will need to go to the holes located directly underneath the cradle and will be directed using vertical metal rods that are not shown in this assembly, but the strings will just slide along those. A shortcoming of the laser cut compartment is that the cradles and motors must be mounted to the compartment base by using bolts and nuts. For the production model, a better solution will be found to increase the aesthetics of the compartment, since this will be placed in the user's home. Here's the current physical prototype model that we have. For the tilting system, the cradles and drums are assembled and already fit well in there. We are waiting on the platforms to mount that motor onto. The blind raising and lowering motor in the middle is attached as well, and we are waiting to put the spool on it. A major issue that we came across during manufacturing of this is that the acrylic is not very rigid when it's this long. The material is strong enough to hold the motors, meaning it won't break, but it does sag noticeably. So if you look closely enough, we had to stack 3 layers of acrylic on top of each other, and this solved the problem for the prototype design. However, for the production model, we will have to analyze different materials and thicknesses of those materials to find the optimal solution for this problem.
So before we move on to the CAD designs for the window frame and window crank operator, we want to talk about the gear force analysis. This was an analysis done specifically for the bevel gears that we use for window crank operator, which were sourced from McMaster Carr. And so using the specifications listed under the website, we were able to just use the shaft angle, module, pressure angle, the number of teeth, face width, and even the input torque from the gear motor that was from one of the previous slides, and we were able to conduct an analysis of the 3 different forces acting on the gear. Now it's important to note that here, because the pinion and the gear are the same exact bevel gear that we're using, the module is 1 for both the pinion and the gear, and so it's important to note that the table on the right shows certain values respectively for the pinion and the gear separately. And so these are the equations that were sourced from the link that you see here on the slide, and we were able to find the tangential, axial, radial force, and also the input torque generated onto the bevel gear.
So this is the window frame design for the production model. As you can see, it is a 24 by 24 inch window, which is a standard size in a regular home in the United States. The right side, you can see 2 buttons that will allow you to interface with the blinds and the windows themselves that will allow you to move the window up and down as you see fit. This will house our blind mechanism box as well. It will be located in the top part of this frame. The blind mechanism box you can see on the picture on the right goes in the top, and it is connected by these end caps here on the left. The blind box will fit into these end caps and it will hold the sides together. And this bracket on the back side in the middle photo will allow the blind box itself to be placed on the window frame and allow for a user or installation process to take just the mechanism on and off, the blind mechanism on and off, without interfering with the window frame itself, as it will already be in place. And to add on to the production model, there will be a thermostat component. As you can see, the thermostat will have a display shown in the middle here, along with 3 buttons. The 3 buttons that are shown will allow for up and down and a mode. So this will allow you to toggle in between modes, whether it's opening a window, adjusting the height of the blinds, adjusting the angle of the blinds. You'll be able to switch between these modes, and you'll be able to set the desired temperature of your house that the windows will seek to achieve on this thermostat. So at the bottom of the window crank, or the bottom of the window frame itself, is the window crank mechanism. This window crank mechanism will allow the window to actually open. It will be motorized, which will open and close the window from the action of this motor here. This motor is connected to a coupler that is connected to a rod and a miter gear at the end. The miter gear is connected to another miter gear, and that miter gear, as it turns, will allow for the user to backdrive the window crank itself, so they can have a manual component. So if somebody wants to physically open their window without going through the blind mechanism product, they can physically do that. A handle will attach onto this top part that will protrude out of this box. And a user will use the handle and regularly operate a window that will allow for a manual component of the window. The motor here sits in the U channel to reduce the degrees of freedom so that it only outputs through this miter gear. And finally, the rotation of the window is controlled through this 3rd miter gear over here that's again attached to a coupler, which is attached to a rod that will open and close the window itself. And here's the physical frame that we have built for the prototype model. As you can see, it is a similar 24 by 24 inch model. along with the other window crank mechanism that is shown on the bottom here. You can see the 2 miter gears that are in place in this image. And there's another rod that will be attached on that will allow for the manual component as discussed earlier. This is the prototype method or prototype product, and the physical production model will follow a similar fashion and form.
Alright, so here we can see our motor retrofitted to the crank mechanism. We attached the miter gear on both the crank operator and the motor and attached them at a 90-degree angle. Although the setup is able to properly open and close the window, we found that at certain speeds the miter gears will misalign and skip some teeth. If we do not change this design, then the miter gears might increase the force on the motors and break it. In order to prevent this from happening, we will be making an encasement that will reduce the degrees of freedom so that the window casement and motor will rotate. And to do this, the encasement will have to use bearings and the motor will be angled at 30 degrees. By using this encasement, the crank operator shaft should no longer have any space to move, which should get rid of the misalignment of the teeth. Here, you can see the crank operator has a crank attached to it to add back drivability. We'll be attaching an 8mm rod to the crank mechanism, and since we calculated the amount of force to turn the motor, the user will be able to open and close the window manually in case of emergencies. We executed the calculations to make sure the motor is back drivable and found that with a gear ratio of 263.7 to 1, the back drivability of the motor is around 0.4325 feet-pounds. A hand-tight crank requires around 2 feet-pounds of force to move, so the user should be able to manually open and close the window. Here, you can see the prototype of the window. You can see the track for the window crank mechanism attached to the bottom of the window. To attach the window to the window frame, we had to laser cut hinges for the window to pivot around. The hinges had to be attached to the top and bottom of the window, but because there was a gap between the pivot point on the bottom hinge, we also laser cut parts to fill this gap so the window does not sag downward and increase the resistance to open and close the window. And for the overall design requirements versus outcomes, our window and blind system is able to move according to the input temperature and light sensors. We were able to incorporate a crank for the back drivability so that the user will have a manual way to open and close the window in case of emergencies. Our current prototype is much bulkier than when we first designed it, and so we hoped that our final product will be much smaller and hidden, and thus more aesthetic. We also plan to hide the wires and electronics below the window frame in the walls so that our product is also more aesthetically pleasing. Our final product will also be integrated so that it can communicate with our house's HVAC systems so that it can reduce the amount of time the user uses the AC or heater. The prototype model is not aesthetically pleasing due to protruding bolts and brackets, and our production model will have these more hidden.
So let's talk about the electrical components of our blind system. So for our sensors, we have two kinds. We have a light sensor, which we're using a light-dependent resistor, a photoresistor, and we have two temperature sensors, and they're going to be the TMP36 analog temperature sensor. And how that works is it takes the relationship of temperature across temperature and voltage across the diode. And for our motors, we have the Never Rest Orbital gear motor, 12 volts. We have two types of motors, one with about 20 to 1 gear ratio, another 263.1 to 1 gear ratio. And then they'll be controlled with the L293DNE motor controller. For our microcontroller, for the brains of the whole thing, we have the Arduino Uno. And for our user interface, which our customers will be using to adjust temperatures, adjust modes, will be a 16 by 2 character LCD and an I2C backpack for ease of connecting to the microcontroller, and some push buttons to be able to interface with the rest of the system. So this is what the general wiring will look like. So we have on the top left corner, we have the temperature sensors connected to 2 analog reads, and the light sensor in a voltage divider also hooked up to an analog read. So that will just be read by the analog read function, and through a series of conversions for the temperature sensor, we can derive Celsius and Fahrenheit from the voltage. And for the light sensor, we're using an arbitrary scale based on measuring what resistance or what voltage we get in darkness and what resistance we get in sunlight, and then we convert that into a scale of 0 to 100 light intensity. On the right side, we have our UI. So we have our LCD and the backpack, which will allow us to use the I2C protocol to communicate with it. And we have some push buttons connected with pull down resistors, and those would be those would be operated by interrupts to determine whether those buttons are pressed or not. And then at the bottom, we have our motors. So 3 motors for our system, 2 for the blinds. One will basically deploy and pull up the blinds, and the other one will control the tilt of the blinds. And then for the window is just to open and close the window. And all of them are being operated by the L293DNE motor controllers. And how that works is we have per motor, we have 2 inputs, which allow us to dictate the direction of the motor. We have the enable pin, which just enables us to control the motors. And then we have the outputs, which we could connect a PWM signal to adjust the speed of the motors, but we will choose not to for this particular project. So once we had the components, we want to test each of them one by one to make sure they operate as intended. So for the light sensor, we just build the voltage divider as we had in our wiring diagram, and we measure the voltage across that divider. And we also want to demonstrate us being able to have a threshold capacity, and we demonstrate that once the voltage across the resistor is less than 0.03 with a 10K resistor, then that LED will turn on. So if we play this video, we see that we successfully have done that, shining a very bright flashlight, about I think 1/3 of the brightness of the sun. We can see that that LED shines. Next, we have the temperature sensor test. So very similarly, we connect analog read to the sensor pin, which is the middle of the TMP36. The right end is to V in 5 volts in this case, and the right side is to ground. And we also want to demonstrate threshold capacity with this, with an LED. So right here, we indicated that 24 degrees Celsius is the threshold. So right now you can see very small. The temperature is about between 18 and 19 degrees Celsius. And if we play the video, you can see I put my finger on the sensor, and you can see that temperature slowly rise. And once it passes 24, the LED will come on. And this is not shown in the video, but if I do let go of the LED, then the temperature will cool down and the LED will turn off. Next, we have the motors, the encoders, and the LCD, and being able to interface with the LCD with a very scrappily put together UI. So here we want to demonstrate that we can measure position of the motor using the encoder, be able to change states through the UI in pressing the button, and control the LCD using the I2C protocol. So go ahead and play this video. This is basically what we've built here is the motor has two states. One state is it moving forward, and the other state is moving, or I should say, clockwise, and the other state is moving counterclockwise. I believe forward is indicating counterclockwise, and reverse is indicating clockwise. And the number below that is the motor position, which the number is basically the number of revolutions from the starting point that the motor is positioned at. So if I go ahead and play the video, we can see it is going, right now it's going counterclockwise, which is indicated by forward. You can see the number going up, and each revolution it makes, it turns into 1. We flip the direction, and once it makes a complete revolution, it goes negative, which we don't actually see here. And how we change state is just a press of a button, which is being controlled by an interrupt. Once we tested all the components, we went ahead and developed the hardware abstraction layer. So the goal here is to encapsulate each of these components into separate files away from the main setup and loop file, and that makes it easy to develop, test, and debug our system when we put together. So the classes we have are a class for the temp sensor, class for the light sensor, class for the LCD, the motors. We have 3 subclasses to allow us to dictate like what is fully open, what is fully closed for each of the components, and then a whole controller class, which we will use to take in air and actually dictate position of our system given inputs from our sensor. So here we have a test using that HAL. This does not have the temperature sensor, but it has basically we can very easily in our loop code declare a couple motors, initialize it with the pins that it's plugged into, and using our get position and set position functions, we can actually set the position of this motor to 0.5 revolutions at 5 seconds of runtime, and at the 20-second runtime mark, we go back to the 0 position. So that's what we will see here.
Here's a demo of the encoder going to position 0.5 at 5 seconds. Okay, we're at 0.5 with an tolerance.
And here we added a tolerance of 0.02 just to give it some wiggle room. And at the 20-second mark, it rotates backwards to the 0 position.
And the actual controller. Calibration is essential because every room will have different thermal properties, so a single controller will not be optimal for every situation. This means it's best to take a few measurements and use that to optimize the control system for that specific room. To calibrate itself, the window will set the blinds and window hinge to their extreme values one at a time. This will ensure the most accurate measurement of the effect of each component. As it's doing this, it will take 4 measurements of temperature to obtain 3 measurements of heat transfer rate. We use a simplified thermal model that includes 3 unknown parameters in addition to sensor values. So once 3 measurements are taken, we can simply solve the system of equations and obtain the complete thermal model. The controller itself will use this model in reverse in a feed-forward to set the desired heat transfer rate. If the room is colder than its target temperature, the window will attempt to transfer heat into the room, and if the room is warmer than its target temperature, the window will attempt to transfer heat out of the room. The target heat rate is proportional to the temperature error. Our simplified thermal model models heat transfer rate in terms of the motor positions, light, and temperature levels, specifically the temperature difference between inside and outside, as well as 3 parameters A, B, and C. The A term roughly represents the effect the blinds have on temperature, the B term represents the effect the window opening has on temperature, and the C term captures any remaining constant offset, for example, from a heat source inside the room. While this model is simple enough that it can't really capture some more subtle nonlinear effects, It has the advantages of being both easy to calibrate for a specific room and easy to solve for desired motor positions given a heat transfer rate. For example, given a heat transfer rate, to set the desired window angle, you subtract the blind angle and constant terms from heat transfer rate, and then divide by temperature difference and the B term. Thus, you obtain the desired window angle directly. Here's a short demonstration of our control system. In the top right corner of the display is the outer window temperature, and in the bottom right corner is the inner window temperature. The remaining value represents the window motor's target position, where a more positive value means a more open window. As the blinds motor is not connected, the system does not attempt to control it. The control system is attempting to maintain a temperature of 22 degrees Celsius. At the start of the window, I'm holding the outer temperature sensor to heat it up. This means that the window's target will be negative to minimize heat gain from outside. As I let the inner temperature sensor cool down, the room becomes colder than its target at 21.8 degrees, so the window target will be very slightly positive to gain more heat from outside. As you can see here, the target refreshes every 10 seconds, and it switched to 0.03. Then, as I hold the inner temperature sensor and let the outer temperature sensor cools down, the window will close to try to avoid shedding heat to the outside, but then, as the inner temperature sensor becomes hotter than the outer temperature sensor, the window will start to open in order to shed heat from the room. This is the intended behavior.
So for the answer section of this project, so we went ahead and so took 6 cases of the system itself. So for case number 1, windows closed, blinds raised. So this is the same thing as simulating as if there's no system in the window at all. So basically, to run back, it's the purpose of these calculations is to kind of understand I guess like the thermal properties and how the window interacts with the environment. So with the outside ambient environment versus the inside environment of the home. So with the windows closed, blinds raised is essentially the same as having no system at all, just like a open window in a home. And so if you look on the left side, we have using equations for thermal conductivity solved out and got a resistance equation for resistance. So R equals dx, which is thickness, over K times A. So K is basically like the thermal conductivity constant of each material, and A is area. So for area, we did 24 inches by 24 inches, which comes out to 0.3716 meters squared. And then for thickness, we just assumed that the plexiglass and also the blinds are the same thickness, which is about 1/10 of an inch, which would be 0.00254 meters. And just for simplification of things, we assume that when the window opens, so when the crank is operated, just certain stages, it would either be open or closed. When it's open, it's tilting out 90 degrees. And when it's closed, obviously, we also are analyzing when the blinds are tilted. So you want to see when the blinds are tilted 90 degrees versus 45 degrees. So 90 degrees obviously means it's completely shut. So the entire window is covered by blinds. 45 degrees essentially means that the blinds are tilted 45 degrees, so some sunlight is coming in, but it is still somewhat covered. And so for the K constants, we used for the wall and the roof, we used plywood and styrofoam. So those K constants came out to be 0.13, and then also 0.033. And then for the floor, we used material marble, so 2.955. And then for the window, we used just essentially glass. But for our actual prototype, we're using just like cheap plexiglass from Home Depot. And then for the blinds, we're going to assume it's PVC wood, which is essentially like a very commonly used material for blinds, which is around, the K cost for that is around 0.2. And when you plug in all these variables, if we go to the right side of the screen, as the first case I said before, it's the same as having no system. So it's essentially just the glass itself. It's just like the window being closed. So you get a resistance of 0.006835 kilo K over watts, I'm assuming. And then you could solve out the equations, doing all the variables, and then you get a thermal conductivity of 0.3716. And writing down all the cases, we have window being closed, blinds lowered, so tilted 90 degrees. So essentially it's the glass plus the wood of the blinds, and then calculate the resistance and thermal conductivity of those. And then going through all the cases, doing the same analysis. And then we were going to take these numbers and basically fit a curve with it. And then we use these numbers in our Simulink to basically more accurately analyze how the heat flows through our system and at certain stages. Obviously, putting in more cases, so essentially like putting in each state, each degree of tilt of the blinds, and each like window tilt degree also would improve accuracy. So just these are like the bare basis numbers that we're using for our Simulink model, which will be discussed in the next slide.
We started modeling our system in Simulink because we wanted to show that our system would be cost effective for customers who bought it. We took an example project from Simulink that provides a thermal model of a house with a heater and added in our system and a cooler, an AC. There were a few bumps along the way as we learned how to use Simulink properly and the limits of what we could and couldn't do with it, as well as understanding the model itself and how we should use it. And initially, the entire system was one block, which made it unreadable for anyone not involved in the work. So we broke it down into multiple subsystems for organization, as well as testing and ease of viewing for people who weren't there, or people who didn't build the model themselves. And also our initial model was binary, meaning that we were only completely opening or shutting the blinds in the window and not having it have a variable position. And so each system was tested in a separate instance to ensure that they worked the way that we wanted them to before testing it out as a whole system using tables to track the results and confirm them, as you can see on the right here. So this is an example of a testing instance, and this table only accounts for 1/3 of the tables for this specific subsystem alone, and so the rest of the testing tables have been left out so that I don't fill up many slides where we're just staring at table after table. And currently, we have transitioned the model from a binary to a non-binary model that can output the current angle of the blinds, the height of the blinds, and the opening of the window. Using the binary model, we had already shown to ourselves that the system was cost effective. And once we work out the few remaining modeling issues that occurred when we converted from binary to non-binary, because the logic doesn't work exactly the same, we hope to show the same results using both the tables and graphs and visual aid.
So for the conclusion and discussion of our project, so for future plans of the smart blind system and with essentially the actual product design of it, we plan to manufacture a more sleek and white design So taking rid of the wood design and putting in like white plastic, implementing a customizable window that fits a homeowner's desired needs for functionality and aesthetics. So for example, we would want to be able to alter the size of the window, changing a wood color. User can do light wood, dark wood, or like either just plain white or black. And also implement remote smartphone control access. So, you can, from your phone, set the temperature of the desired home temperature, and also manually opening and closing the windows and blinds remotely from the phone. So using our smart home system, it removes the worry about maintaining the temperature of a homeowner's house and the worry about turning on and off HVAC systems. So in the end, the user eats the cost upfront of the system, but will break even in about 9 years. We just did a couple calculations, using the average yearly cost of using HVAC systems in a home, in an average home in like a very, very cold Midwest area, and found to be breaking around 9 years. So for the design and general learning curves, we realized that simulating a completely accurate real life heat flow through the window is really challenging, because not really anything can be completely airtight and completely insulated. So insulating the room was a little unrealistic and therefore captures unrealistic capabilities of our system. Heat will escape and, cold air will flow into the home, no matter what we could possibly do for the project. But, with more money and more time, we would be able to implement more accurate and advanced insulation materials, be able to like line it with like weather repellent tape around the window itself, to prevent heat from escaping or from cool air to enter the home. And yeah, that is our project in a nutshell.